Swayam Prabha. Digital India. Educated India.
Okay, so we'll talk about Rabin crypto system, which is based on the what is called Chinese remainder theorem and quadratic residue. So before going to the Chinese remainder theorem, we want to see what is the how to solve the system of linear equation modulo p. So system of linear equation modulo some p or n. So basically we have some system of linear equations, say a1 1 x1 plus a1 2 x2 x3 a1n xn equal to b1. This is first equation. Then the second equation is this a22 x2 plus a2n xn equal to bn . Suppose there are m equations. So a m1 x1 plus m2 x2 a mn xn equal to, sorry, this is b2 bm. So this is a system of equation. There are m equations, n unknowns. So this we can write in the matrix form, as you know, a11 a12 a1n a21 a22 a2n am1 am2 amn, and then this is the x vector and corresponding we have b vector. There are m equations, and this is modulo n, means we are taking each of aij is coming from Zn. So and also bij is coming from Zn. So we have to find the solution for this. So we have to find xij such that which is coming from Zn, which satisfy this system of equations. So that is the problem. So to solve this, we know we have to check the rank of the augmented matrix is same as rank of the matrix, and those are the concept there. So let us take a simple example how we can solve this type of system of linear equations modulo some prime. Okay, so we will take an example. So suppose we have this system 4x plus 7y equal to 9 and 5x plus 2y equal to 3, and we have to solve this system of equations modulo 13. So our n is equal to that modulo 13. So how we can solve this system? So we can multiply this by 4 inverse mod 13, and then so this is equation number 1, equation number 2. So basically 4 inverse mod 13 is basically how much? 10, because if you multiply 10 with 4 it is 40, then if you take the mod 13 it is 1. So that is basically 10. So we multiply this with this 10. So this will be, so 1 become x plus, then this is 10 into 7. So this is basically 10 into 7. So we multiply this equation by 10, that means 4 inverse mod 13. So 10 into 4x plus 7y is equal to 10 into 9, and every operation is under mod 13. And similarly we know that 5 inverse mod 13 is how much? 5 inverse mod 13 is basically 8. So what we do? So, then we multiply this equation by 8. So, 8 into 5x plus 2y is equal to 8 into 3 mod 13. Every operation is under mod 13. So, if we just multiply this, we will be getting two equations, x plus 5y equal to 12. This is coming from this equation, and from here we are getting x plus 3y equal to 11. Now, if we subtract, we are getting 2y equal to 1. Now, y is equal to 2 inverse mod 13. So, this is basically 2 inverse basically 7, because 2 inverse mod 13 is basically 7. So, we got y as 7. Okay. So, now once we have the y, then we can put this value into one of these equation, either this or this, and we should able to get x. So, then x is basically, so from here x is basically 12 minus 5y. So, 12 minus 5 into 7. So, under mod 13. So, this will give us 3. Okay. So, basically we got x equal to 3. So, this is the solution of this system of equation modulo 13. Okay. So, now if we want to if we try to solve this in matrix form, so and we have to perform the matrix operation like row operation, column operation. So, we can try that also. So, our equation is basically what? Our equation is 4x plus 7y equal to 9 and 5x plus 2y equal to 3. So, this we can write as 4 7 5 2, and if we take the augmented matrix, this is the, so we have to perform the operation on this matrix, and we have to row operation, and we have to make this 1 0 0 1, then that will give us the solution. So, to do that, what we do, we perform the row operation. So, basically we perform R2 is going to R2 minus R1, and if we do that, we will be getting this R1 is remain same, R2 is, so 1 minus 5 minus 6. Now, this has to be under mod 13. So, if you take the mod 13, so this will be basically 4 7 9, this is 1, this 15 is basically 8, and this 6 is basically 7 under mod 13. So, now this is the current position of that augmented matrix. Now, we have to make it, so now we have to perform R1 is going to R1 minus 4 R2. So, R1 is going to R1 minus 4 R2. If you do so, we will be getting 0 1 7 1 8 7. Okay. So, now we want to make it 0. So, for that we have to perform this operation, and every time we are doing mod 13. So, we are doing R2 minus, so this we multiply by 8, and then R2 is going to R2 minus 8 R1. If you do so, then we are getting 0 1 1 0 7 3. So, from here also we can say x equal to 7, sorry, x equal to 3 and y is equal to 7. So, this way also we can solve this, but every time our operation should be modulo operation under that, here it is 13, in general it is n or p, under that p. Okay, now, the Chinese remainder theorem. So, basically we want to have a system of modular equation, and we have more than one equation and we want to solve that. Say for example, suppose we have, this is one equation, A mod n and x is congruent to B mod n. So these two is the modular equation we have, and here we are assuming GCD of Mn are 1. So that means M is relatively prime. This symbol we can use as relatively prime to n, both are relatively prime to each other. Suppose we have this type of system, then what is the solution? So Chinese remainder theorem will give us the solution. Not only one system, we may have many systems. So but let us start with one system. So how we can solve it? So let us take an example, like say we have x is congruent to 3 mod 5 and x is congruent to say 5 mod 7. Okay. So now we want to have this is equation 1, equation 2. So we want to have a solution for this system. So we want to find the value x which satisfy both the equation. So the x which satisfy equation 1s are basically all the integers from this 3, 8, all the integers which we try to divide by 5, remainder should be 3. So 3, 8, 13, 18, 23, 28, 33, 38, so on. So this is the all x which satisfying equation 1. Okay. Now similarly, so this is say A set A1. So this is the all x satisfying equation 1. Similarly, we can find the all x which satisfying this equation 2. So those are basically all the integer. If we divide it by 7, it should give us 5. So 5, 12, 19, 26, 33, 40, like this, A2. So A2 is the set where all the values satisfy equation 2. Now we want the solution which satisfying both the equations. So that is basically the intersection, A1 intersection A2. So this one is the x which satisfying both the equation. So this is basically 33. So this is basically any two number, any two element in this intersection differ by a multiple of 35. So any two element in A1 intersection A2 differ by a multiple of 37, which is basically this 5 into 7. Okay, that we can easily verify. If you take any two point, then they should differ by a they will be differ by a this. So this is the 37 is the solution for this 33. 33 is the solution for this system mod 35. So this x is equal to x is congruent to 33 mod 35. So this is the solution for this system of equation. Now you can easily verify this is because this is satisfy this equation, this is also satisfy this equation. So this is the naive way, but we need to know how we can, in general, how we can get the solution. So suppose we have the equation like this, the general form, x is congruent to A mod n and also x is congruent to B mod n. So now we want to find out the solution for this. So say we are taking this as equation 1, we are taking this as equation 2. Now, the x satisfying equation 1 will be of this form, x equal to a plus some t into m, where t is a positive integer, or t is an integer. Okay, so any x of this form is a solution of solution of equation 1. Now, we want this to be also solution for equation 2, then only it will, that x will satisfy both. So, we need to find t such that this a plus tm will satisfy this equation also, second equations. So, if we have to do that, so a plus tm, we need to find t such that, so if it is satisfying this equation, then it should be written as, this should be written as b plus some s into n. Okay. So, now the question is how we can get n. So, we can take this that side. So, Tm is equal to b minus a plus Sn. Okay. So, now basically if we just, so T is basically m inverse b minus a mod n. So, basically we need to find m inverse mod n, m inverse mod n, yes, and then n inverse mod n means, so that inverse with this m will give us is congruent to 1 mod n. So, that is the definition of inverse. So, if m inverse, so m inverse mod n will exist because this is the guarantee, because GCD of m and n are 1. So, that's guarantee that inverse will exist. So, this inverse we can calculate by extended equilibrium algorithm. So, once we got m inverse, so then we choose T as like this, m inverse b minus a, obviously mod n. And if we choose T as this, then it will also satisfy equation 2. So, then this is satisfying both equation 1 and equation 2. Okay. Now, we just calculate this by the previous example. So, our equation was x is congruent to 3 mod 5 and x is congruent to 5 mod 7. Okay. So, so basically this is our A, this is our M, this is our B and this is our N. Okay. So, now the question is how we can get the solution. So, what is M inverse mod n? So, M inverse mod n is basically, M is basically 5. So, 5 inverse mod 7. So, 5 inverse mod 7 is basically 3, because 3 into 5 is basically for 15. So, 15 mod 7 is basically 1. Okay. So, now T is basically M inverse. So, 3, so this is M inverse b minus a mod n. So, M inverse is 3, what is b? B is 5. So, 5 minus 3 mod 7. So, this will basically give us 6. So, the x is basically a plus t into m. So, 3 plus 5 into 6, 33 mod m into n. So, that is 35. So, this is the solution coming from this. So, this is the Chinese remainder theorem for two equations. Now suppose we have general case, I mean we have many equation, more than two equation, then the question is how we can solve it. Okay. So that is the Chinese remainder theorem. So Chinese remainder theorem. I mean this is the general form of the Chinese remainder theorem. Suppose we have R equations, x equal to a1 mod m1, x is congruent to a2 mod m2, x is congruent to a3 mod m3 dot dot dot, x is congruent to ar mod mr. So suppose there are R equation in the system, we have a system of modular equations and there are R equations, and here we have some conditions on this M. So this set M's are mutually co-prime. So this MI's where MI's are pairwise co-prime. So that means GCD of MI MJ is 1 for all I not equal to j. So that means MI is co-prime with MJ for I not equal to j. So that condition must be there for this system to have the solution. Not only solution, it will have a unique solution under mod of this product. So we have seen for 2. Now it is a general case, and after that we will take an particular case for 3 and we try to solve that. Okay. So suppose we have this system, and then it is Chinese remainder theorem is telling this system has a where this, then the system has a unique solution earlier solution was 33, because if you take any other solution that will differ by the 35. So if you take mod of that product 5 into, so this will again give us 33. So that's why it is unique. Okay, because every time if you take any two solution, they will be differing by that product. I mean 7 into 5, 35. So that means if you take that solution mod 35, it will give us 33. Anyway, so this system has a unique solution mod under mod M, which is basically this product M1 into M2 into MR. So this system of equations has a unique solution under this. So now the question is, what is the form of that solution? We will just write the form of this solution. The form, that unique solution is basically x equal to summation of ai mi yi, I is equal to 1 to r. So ai we know, and what is mi? Mi is basically this capital M by small mi. Basically in this product the mi is missing. So this is basically all the elements other than all the primes, not primes, all these numbers. So mi minus 1, then mi plus 1 dot 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 mi. So mi is missing here. Okay, and yi basically this mi inverse mod mi. So this is the solution of this system of equations. Okay, this system of equation has a unique solution. This is the solution. Okay, now the question is, how we can execute this. So, we will take an example, we will take 3 equation, as 2 equation we have seen how we can tackle. Now, we take 3 equations and then we will try to get the unique solutions by Chinese remainder theorem. Okay, so let us take 3 equations. Suppose x is congruent to 4 mod 29, x is congruent to 7 mod 30, x is congruent to 8 mod 31. So, this is 3 equations, r is equal to 3 here. Okay. So, now the question is how we can solve these equations. So, we will use the Chinese remainder theorem. So, we know the solution for general case, but we will derive this. So, how to solve? So, this is equation 1, equation 2, equation 3. So, we have seen the example where we can handle 2 equation at a time. So, what we do? We take 2 equation at a time, then we get the solution which satisfy that these 2 equation, then we will take that solution along with this equation. This is also 2 equation. So, we will take 2 equation at a time. So, we first take these 2 equation, equation 2 and equation 3, and we apply that technique a plus a plus tm and t is equal to that form. So, if you use that, so this is a, this is b, this is m, this is n. So, the solution will be basically, so for that we need to find out this is m. So, for t we need to find out m inverse mod n is 31 here. So, if you calculate this, this is basically 30, you can verify this. Now, so t is basically, if you remember that form, m inverse, this is m, this is n, this is a, this is b. So, m inverse b minus a mod n. So, if you just put this value, m inverse is 30, b is basically 8. So, 8 minus 7 mod n basically mod 31. So, this will give us basically again 30. Okay. So, x is basically then a plus tm. So, t we got, m we know. So, x is this mod m into n. So, this is basically this is 7 plus 30 into 30 mod. So, these two, if you multiply these two, we will be getting 930. So, this is basically coming out to be 907 mod 930. So, we have the solution for these 2 equations. So, these 2 equations will give us the solution x equal to 7 mod 3. Okay. So, now we have a equation this 4 and we have equation 1. So, now again there are 2 equations and we can easily verify because these were mutually co-prime. So, now this is also will be co-prime through this. So, now this is m, this is n, this is a, this is b. So, now we need to solve these 2 equations by the similar fashion and that should give us the solution. So, let us try that. So, now our equation is, now we have this is one equation and another equation we have, the first one x equal to 4 mod 29. So, this is now a, this is m, this is now b, this is n. So, to get the solution we have to find out m inverse. So, 29 inverse mod. So, this again by Euclidean algorithm and we know these two are relatively prime. So, inverse will exist and using extended Euclidean algorithm one can get this. This is the inverse. Now T we can calculate. T is basically M inverse into B minus A. So 449 into B minus A mod n mod. So this will give us basically, if we calculate, 897. Okay. So now x equal to what? X equal to A plus T m mod m into n, these two. So basically it will be 4 plus A is 4. Now T we got this and m is this. So 97 into 29. So this if we calculate, this will give us 26017 mod this product. So this is the unique solution. We are getting 29 into 30 into 31. So this is our x. So this is the way we solve this system of equation. If you have 3 equations, so this the so we take it 2, then we solve it, and with that solution we again solve with this equation. So this way we will continue. If you have more equation, we will continue this process. If you have another equation, we will just take that one with this and we will get the solution. So that will give us the solution for the Chinese remainder theorem. Thank you.